Hello everyone, am I audible? And my screen is also visible, right? Okay, so let's start today's lecture. So it's basically on interactive problems. So what are interactive problems? So basically when you take input, give some query or give some output and the system takes that and gives you the next input. So it's like an interaction, not like just you get an input and you just give an output, right? So you need to constantly interact with the system, and there are also various kinds of interactive problems, and we will be looking at some of them today. So first is from the code forces, and second is from Olympia IOI, or past IOI problem, which was also there in the set which they provided. And one important thing when you write the code of interactive problems, whenever you ask a query or do something, you need to flush the output. So in C++, you can use cout.flush or just endl, but in other languages there are other commands. So let's start with the first problem, which is take a guess. So basically in this problem, you are given, and basically the person has n elements, a1, a2, a3, an, and you can ask that person who don't know this array, you just know the size of the array, which is n, and your objective is to find the kth smallest element in this array without, like, you don't know the array initially, right? And you can ask queries where the first one is give two indices I comma j, and the system will return ai and aj, and the second is again give I comma j and the system will return ai or aj. So and when and or are bitwise operators, bitwise and bitwise or. So now you have at most two n queries you can ask, and then you need to find the value of the kth smallest element. So how can we solve this? So basically there is a very good property where suppose you have two integers a and b, and if you find if a suppose 0 1 0 1 0 0 1 and b is 1 0 1 1 0, so 1 1 1 1 0. So if you find the AND of bitwise AND of these both, then it will be 0 1 0 0 0. This is A and B. And if you find A or B, then it will be 1 1 1 1 1. Right. So we can see that when these both A and B have a bit set, we get 1 in AND, while when any of them have a bit set, we get 1 in OR, right? So what if we do this addition, a and b plus a or b? So suppose for we take some bit I, so if we take a and b and a or b addition, so suppose if both are set 1, then in a and b this bit will be set, and in a or b in this bit will be set, as we saw in this in both A and B and A or B it's set. But suppose only one of them is set, then it will only be set in A or B, and in A and B it won't be set, right? So, and when both are not set, it won't be set in any of them. So you can observe that the number of times it is set in A and B. So suppose it's set in A and B both, or just A or B, or just or none. So it's either it's set 2 times, 1 time, or 0 time, and if we add them, then the number of times in the addition that bit is set is 0, 1 or 2. If both are present, then it's in A and B and A or B both. So you can add that. So here basically we get that for any two integers A comma B, A and B plus A or B is A plus, right? So suppose we take some example 5, uh, ah, no, this is 12, and we take this is 6, right? And now we find A and B. So we get and is nothing but 0, 0, 1, 0, which is 4. A or B is 0, 1, 1, 1, which is 14. And if you add both, you will get 18, which is A plus B, right? So this property can be used over here. So how can we use this property? You have two n operations, right? So basically you can take two adjacent and find A or AI and AJ, AI or AJ, and basically the sum you found out. And if you have sum of A01, A12, A23, like this n minus 1 sums you have, then you have more two operations, and after that you should find the array. So what can we do? So suppose I know A, B, C are my three consecutive elements of the array. A, B, and C. I know A plus B. I know B plus C. So what can I do is I will query A and B and A or and C and A or C. So I will get the value A plus C using two queries. So these use 6 queries, right? And after knowing this, if you add all these, you will get 2a plus 2b plus 2c. So if you divide it by 2, you will get a plus b plus c. So now you also have the value of a plus b plus c, and you also have all these three things. Then you can see that AB and A plus B plus C. So actually you can remove AB, the sum of A plus B from this A plus B plus C to find the value of C. Similarly, if you remove this, then you get the value of A, and if you subtract this, then you get the value of B. So you just took 6 queries, and n is 3 over here, and the minimum n is 3, so it should work for more than 3 as well. So you just took 6 queries, so which is 2n queries, which is under the limit, and you found out A comma B comma C, right? So you actually found out the array. Now once you know the integers A, B, C, then there are more integers over here, right? So suppose this is D, E, F dot 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 dot. Now if you query AD, so basically A and D and A or D, you will get A plus D. And you also know the value of A because we found out in the previous one using three elements, right? We know the value of A and B and C. You can find the value of D by subtracting the value of A. And similarly, you can do this for all the elements of the array, and you will get the elements of the array. So once you have the elements of the array, you need to find the kth smallest element. So basically sort the array and find the kth element in the sorted array. Yeah. So it's order of n log n because of sorting, and at exactly 2n queries. Anyone has any doubt? Okay, then I will proceed with the code. So it has quite simple code. So one thing you can do is you can just make functions so that you don't need to again and again put C out, and it looks easy to understand, easy to debug. So ask or is finding or of two elements I comma j, and there in the question it's two based indexes, but I've used one base, so we'll come to that. So you just take n and k, then you find AB, which is ask or of 0 1, BC is ask or of 1 2, and AC is ask or of 0 and 2. So basically just taking the first three elements, and the capital ones are basically same of add. So once you do the sum AB, BC, AC and AB, BC, AC, so basically you are taking AB plus BC plus AC in total, and if you divide by 2, then you get A plus B plus C. Now you have this sum, you subtract B and C, B plus C from the sum, you get 0th position. When you subtract A plus B, you get the first position, and when you subtract A plus AC, you get, okay, this should be interchanged, but it doesn't matter since at the end you got the element in your sorting. And as you go, you find the sum of the 0th and the ith position, and then just do uh, the current sum minus array of 0, which is the first position, so you get the current value, sort it and print the k minus 1. And this endl is very necessary, else it will give idleness time limit exceeded, because until you print it, if you put the other way of putting, like a character way of putting endl, then it won't, it just goes to the next line, but it doesn't print it. Endl in C++ prints it, or you need to flush the output to flush whatever output you have printed. Yeah, hopefully that's clear. If anyone has any doubt, then they can ask. Thank you. So now we can go on to the next problem. This is an Olympiad problem, unscrambling a messy bug. Okay, so it has a bit long statement, but let's let's start. So basically, you have an array A1, A2, A3, A4, A5, and this basically are in the form of bits because they are two large integers, so they are like bits. So A is a string of bits 0 1 0 1 1 0. Similarly, everyone has string of bits of size n. Each bit, each string has a size n, and they are bits. And this array you need to put. So it's like it's a bit different, not the usual code forces one. But here, what you need to do is you need to put this array, and what the judge or the system will do is for they will have a permutation p1, p2, p3, pn, and exactly n is the size which you need initially. And suppose you have uh, suppose you have bits b0, b1, b2, bn, right? These are 0 or 1. Then what will it do is it will shuffle each and every element, each and every a in the set, and it will take each and every a and it will shuffle its bits by making them b p0, b p1, p p2. So basically for the 0th position, it will take me assign it the value of p 0th position in that current set b, in that current string b. So if the string is 0 1 1 0 1 1 0 1 0, and P is 521034. Then this is suppose A0. Then this position will be fifth position, which is the last position, which is 0. This position will remain, will be second position, which is a 1. This position will be first position, which is again 1. This position will be zeroth position, which will be 0. This position is 0, 1, 2, third position, which is 0. And this position will be the fourth position, which is 1. So it will shuffle it like this. And this process it will do for each and every element which you add. It's on you which elements you need to add. And then they ask you to do query, and in each query you can give again a string of length n like this, and you need to, they will tell if that is present in the set or not after they have did this fixed shuffling of each element, the bits of each element. So after shuffling it becomes this. So after shuffling, if you ask if this is present, then it will be 0, that means it's not present, that's false. And if you ask this, then it will be 1, right? So this is the question, and they now ask you to find this permutation P, right? And there are some subtasks as well. This is the adding element compile, which you run, so that after that they will shuffle the bits. And this is checking element, and then you need to return P. So let's see on the constraints. So the first approach, the basic approach that you might think would be like, you have an element. So first thing you might think like, okay, I put 1 and everything else 0. Then I just loop, make each and every bit 1 and others will be 0. So you find where this position goes, right? So whenever I find that this is 1 and this all 0 and it gives true, that means this position, that was only the one position, goes here. So I know the value of this. Now the next element that you input to find the second value would be 1, 1. So and other all 0, right? So again, you know that this p of 0 equals to some value. So you keep that always set, because you know this is set, so it will go that there. And for this value, you loop this each and every page, making that bit 1 and all every other bit 0. So and you check if it gives, suppose it gives 1, everything 0, this gives 1, then you know that the position it goes is there, because you know that only 2 bits were set and 1 bit you already know the position of. As you have seen here, only 1 bit was set there, so you only know wherever it goes, that will be P0, right? So now this is the easiest approach. Whenever you see the problem, you might think of that, that's the increasing as you go. And this approach will give you the first subtask, right? Because if how what is how many questions do you ask? So basically, you just put n strings you put in, and you go loop n for the first time, n minus 1 for the second time, n minus 2 for the third time. So it's nothing but n into n plus 1 by 2. So that's nothing but order of n square, and you can see that here you are actually getting n square, right? Here you are actually getting n square for the first subtask. 8 square is 60. No, it's it's so next is, you still have a very high R, which is the number of asks that if that is present or not can be there. and you have smaller value of number of words you can put. So what we can do is, if we just, instead of looping it 1 to n, if you just do some randomization on that, then it will decrease to n into n minus 1 upon 4, and that should pass this second subtask. But the third one, R is not, so you can't do since the third one, or the third one. Yeah, so those are the basic ones. Now let's go on to the main one, full solution. So the thing you need to observe in the full solution is n is 128, right? Which is to the power 8, 7 or 8, and if you multiply that with 2 to the power 7, and if you multiply 7 to n, then you get 896. 7 with 128, which is 2 to the power 7, you get 896. So what this will indicate, this might indicate, is you can divide it into half and solve the problem, which is divide and conquer in binary, like binary search, or you can merge single component as you do in set tree and go. It can be one of them. Uh, the one which looks practical is divide and conquer, because you want each and every element and not sum or something. So that looks solver, or it can be like binary lifting, and 1 2 then 4 then 8, like that. So it's based on some binary, you can get the hint by that. Now what can it be? So we need to use, first of all, it's a full solution and it's IY problem, so you need to use each and every information. So you need to use ones and zeros. In the initial approach, we just ignore the zeros, and we need zeros and ones both, and we need to use those optimally. Right. So now what we can do is, we know that we need to divide each and everything by half. Now how can we do that? So suppose we have like 1 and everything else 0, then we get to know where this position is. So what if it goes over here, then I know that p of this position, p of I is 0, because it takes some element from 0, right? But this is just solving for 1. What if I need to insert more, because they have kept place for more insertions, right? So of course I can't waste that, because I need to use each and every resource I have to for solve the full problem. So what if I add 1 2 3 4 5 6? Yeah, we'll take for n elements, 8 elements initially. So we can add 1 0 0 0 0 0 0 1 0 0 0 0 0 0 1 0 0 0 0 and 0 0 0 1 0. So basically we are adding half, for the half elements we are making it 1 with only a single bit, because if we keep more than one bit to search, suppose you have 1 1 0 0 0 0, and if you don't know both of these bits, then for searching that you will take n square operation, approximately n square operation, because for each search for this you need to find each search for that, right? So actually that's not allowable, so you need to search in order of nearly n itself, right? So that makes it clear that you can have exactly one unknown set bit that you search. You cannot have more than one unknown set. So if you do like this, and then again you go on each and every position and check if in the final array is that bit set, like if I ask 0 0 0 0 0 1 0 0, is this present? If this is present, That means I know that P of 5, which is the position we have, is from the first four elements, right? So is from 0 to 3, right? And if that is not present, that means this is from 4 to 7, right? Because we know that initially we are keeping one set for half of the elements, so half of the resulting in the set will be true, and that will have actually the value from 0 to half, which is here for example of n is 8, 0 to 3, right? So this way we can find out which P is in the first half, for each position, whether P is in the first half or P is in the second half, right? So now what our problem is, we have two sets, right? And we know that at each position whether P is in the first half or P is in the second half, right? So what can we do is, suppose now again leave the previous operation. Suppose we had this half array and we did the same thing for the half array. So 1 0 0 0 0 1 0 0 we input, right? And we loop through the same thing and we check if this is present or not. So we can actually do the same method and divide it into this half or this half, right? And same if we do 1 0 0 0 and 0 1 0 0. So actually input is 1 0 0 0 0 0 0 0 0 0 1 0 0 0 0 0 0 0 0 0 0 1 0 0 0, because now we are also checking, making, dividing this half into two and this half into two, because initially we have divided 0 0 0 0 0 1 0 0. If we ask this and then again we search, and if we know that the ith bit is set, then I know that that is either from this half, this half, or from this, right? And we also know that previously when I checked the ith bit, it was either from the first half or from the second half. So if it's from the first half, then it's this part. If it's from the second half, then it's this part, right? But similarly we can go down and solve the problem. So next time we'll literally half and we'll get each and every value. But the problem over here is that you can't again put this, because you have already put this in the previous, for the first time when you loop, right? And you only loop n times, because already you are you have log n times you need to loop each and every position to find which half p of I belongs to. So what you can do is, when you are, the only thing we know that we have this as an array, right? And these all are waste elements initially, right? So, and this size also changes as we go down. If you go down, so you have four parts, each has two elements, then I know that waste for this is, this all is waste, right? Waste for this is this and this. So every time the elements which you don't want actually changes, right? So what you can do is, you can keep this element 1, right? So now you know that you have how many bits set. So it's actually n by 2 bits set, which is the waste element, plus 1 which is, you set that. And each time you know this, you can actually keep, when you are finding it, you know that this element is from the, you know that for each uh, loop actually you can keep the waste element. So suppose you are finding p of 0, or you know that the element is from the first half, the ipi is from the first half, that you know, because you know either they are from second half or first half, right? So if pi is from the first half, then you just need to make all the second half elements 1, right? So and each time the n, this n upon 2 bits will then become, I have this as well, right? So each time the number of set bits increases, and you know that initially they are in which part. and according to that you can set those paths zeros and all other paths one, right? So this way you can get uniquely, you can add elements, and uniquely you can determine the position. So yeah, that's the approach for it. So you have order of n log n questions and order of n log n addition. uh, any questions about it yet? Okay, then let's go on to the code. So basically this is the final answer. Initially you put, and so basically this is a recursive function put, and this function is very important because as you put you will use that over here as well. So initially if you know that this is the final, basically r is nothing but, I've not included r in my range. So if r is l plus 1, so basically this is the single element, so you can't actually divide this into two, so you don't have to put anything. Else you have the division, and then what you do is you keep everything one, and then you remove the from L to R, which is the current range. You make the value 0, and then till the middle element you make the value 1, add that element, and then again make the value 0. So this is the only set bit you add, and then again make it 0. So next time at most only one bit in this range will be added. Then you add, this is base by mistake probably. So then, and then you put you function in for L to M and midpoint to R. But this is how you put the element. Now we need to solve it. So after putting it, we have the initially. So basically, these are the positions of the indices, right? These are, so currently you in the range you have, from for range 0 to n, you have all the indices within those, right? And then you solve. And in solve, this is the range of indices you have, and this is the range in which these indices are, right? So this is the base case. So basically if this is if the range is only a single element, so you don't need to divide, and you know that answer for the indice which is in this range, so basically this is the will be n, right? So we will get that as we first see how we are dividing, right? So this is the midpoint, and again you make everything one as you did here, and then you make for the all the positions which have, so basically, yeah, so basically we are going a of p of 0, so we are taking it from some position, right? So once we have taken it from that position, here what are we checking? If that is this position there, so if this is set, that means the value of this position, value of p of I, is still half, right? And if it not, then it's in the other half. So here we actually remove all the indices which are here and make it 0, and for each one, so initially you loop through 0 to n, and you make this one, and if you check if it's there, then in the first half you have the this position, right? So it's in the A element, and it's in the B element, because else it's in the second half, and then you again make the current position 0, right? So suppose you have you have 1000 and 0100, and permutation is 010312, right? Then this will be p of 0 will be 1. So basically this will the reshuffled array ones will be 1000, because this will be the zeroth element will be same, and this will be the second one will the second position will be on the third position, right? So 0010 will be the reshuffled one. So when you ask at each position, you check if this is set. That means this position has the p of ith in the first half. So this position has p of I in the first half, right? So you put this position in the first half because this has the p of I in the first half, right? So now for each position in A, you know that the value of p of I is in the first half, and for each position in view that you put in B, the value of p of I is in the second half. And then when you make the half and then you go for example on the left half, then you know the values, like the positions which have the p of value in the first half. So you make those positions 0, and then you select make it 1 to those positions only, because now you have a fixed range of elements, right? And when you have left with the only position, you know that the value is n. Yeah. Anyone has any doubt? Yes, there can be an interactive problem in finding. So that's for today. Thanks everyone for attending.